Hello everyone, and thanks for joining us on today's webinar. My name is Amin. I am an Alpha Application Engineer at EMWorks. Today, we'll be talking about how to design an efficient wearable antenna. Before we begin, I would like to give you a brief overview about what we are going to discuss today. First, I will briefly talk about wearable antennas and the challenges involved in their design. Then, we'll look at a case study of millimeter wave wearable antenna. At the end, we'll have a live demo. In case if you have any question, I'll be happy to answer them at the end of the presentation. Before we proceed, I would like to take a moment to introduce EMWorks. EMWorks is a leading provider of electromagnetic simulation software for electrical and electronic designs from DC to millimeter wave frequencies. Our products are embedded in the most popular CAD platforms, namely SolidWorks and Inventor. They cover a very wide range of applications ranging from electric motors, generators, transformers, and power electronics to antennas and various wireless circuits and components. HFWorks is an antenna and electromagnetic simulation software for RF, microwave, millimeter wave, and high-speed digital circuits. It uses state-of-the-art finite element solvers and machine technologies to compute fields as well as antennas and circuit parameters. It also comes with an integrated electrothermal solver. To learn more about our products, please visit our website at www.emworks.com. Now, let's dive into wearable antennas. Wearable antennas are small antennas that can be integrated into clothing or accessories such as smartwatches, headbands, and even jewelry. Wearable antennas have a broad range of applications across different industries. In healthcare, wearable antennas can be used to monitor vital signs such as heart rate, blood pressure, and body temperature. They can also be used to track patients' movement or location, which is useful in medical facilities and for patients with conditions that require constant monitoring. Fitness and sports enthusiasts have also started to incorporate wearable antennas in their training routines. These antennas can track performance metrics such as distance traveled, calories burned, and heart rate. They can also be used for location tracking during outdoor activities such as hiking and running. In the field of communications, wearable antennas are rapidly gaining popularity. They can be used in mobile devices such as smartphones, smartwatches, and other wearables to provide high-speed data transfer, voice communication, and GPS tracking. Wearable antennas have made it possible for people to stay connected on the go, making communication more convenient and efficient. Wearable antennas have also found significant applications in military and defense. They can be used in military applications such as soldier tracking, communication between soldiers and drones, and other battlefield applications. Finally, wearable antennas have also made their way into the entertainment industry. They can enhance the user experience by providing more immersive experience in virtual reality and augmented reality applications. Now we have talked about wearable antennas. Let's now examine some of the difficulties associated with millimeter wave wearable antennas. Millimeter wave wearable antennas have gained significant attention in recent years due to their potential applications in various fields, including healthcare, sports, and entertainment. However, the design and implementation of these antennas present several challenges that need to be addressed before they can be widely adopted. One of the most significant challenges in the design of millimeter wave wearable antennas is their proximity to the human body. Wearable devices are often worn on or near the body which can result in a significant change in the antenna's radiation pattern and impedance matching. This effect is especially pronounced for millimeter wave antennas, which operate at higher frequencies than traditional antennas. The human body's complex electromagnetic properties can significantly alter the performance of millimeter wave antennas, leading to signal degradation and reduced range. Another challenge is ensuring that the wearable antenna is comfortable and practical for everyday use. Wearable devices must be lightweight, flexible, and conformable to the human body to avoid discomfort or injury. Safety is also a significant concern when it comes to wearable antennas. The high frequencies used by millimeter wave antennas can potentially cause harm to the human body, particularly at close distances. Thus, it's crucial to ensure that wearable antennas don't exceed the limits of the specific absorption rate or SIR, and that they don't cause any thermal or non-thermal effects on the human body. Finally, atmospheric attenuation is a challenge that affects the performance of millimeter wave antennas. The presence of rain, fog, or dust can significantly attenuate the millimeter wave signal, reducing the range and the quality of the communication link. Alright, now let's look at a case study of millimeter wave wearable antennas. The antenna substrate is composed of taconic TLY, which has permittivity of 2.2 and loss tangent of 0.0009. The antenna is designed to operate between 57 GHz to 59 GHz. Millimeter wave communications, which utilize a wide unlicensed frequency band of around 60 GHz, which typically ranges from 57 to 64 GHz, has drawn great attention because it can accommodate data rates higher than 1 gigabit per second. The antenna consists of 3 layers, including ground, patch antenna array, and parasitic elements. The impedance transformer between the 50 ohm line and the first patch is used for impedance matching of the patch antenna. The second patch antenna is excited by 50 ohm series feed line. The parasitic elements are fed by the electromagnetic coupling between the 50 ohm line and the parasitic element. The patch has a dimension of 0.3 lambda by 0.3 lambda. Today, we'll explore 3 different scenarios: antennas with and without parasitic elements, as well as antennas on Google Glass. First, let's analyze the performance of the antenna without parasitic elements. Based on the two plots, we can observe that the antenna array performs well within the range of 57 to 59 GHz. The antenna elements are well isolated, exhibiting insertion loss of less than -20 dB, as you can see from this plot. On the right, we can observe an electric field animation at the resonant frequency. The antenna has a high gain of almost 17 dB with broadside radiation. Now let's look at the performance of the antenna when the parasitic elements are added. The parasitic elements, as we said before, are fed by electromagnetic coupling between the 70 ohm line and the parasitic element. As we can see from the return loss plot, the resonant frequency of the antenna does not change significantly when the parasitic elements are added. Now let's look at the radiation pattern of the antenna with the parasitic elements. As we can see from the 3D radiation pattern on the right, the antenna has a maximum gain of almost 16 dB. Looking at the 2D radiation pattern on the left, we can see that the radiation pattern of the antenna without the parasitic elements has radiation null at around 16 degrees, as we can see from the red plot. However, the radiation pattern of the antenna with the parasitic elements has now null at around 60 degrees, demonstrating the advantage in terms of the antenna coverage. So for example, the antenna without parasitic has a null, as we said, at 60 degrees. So for instance, when we have, let's say, signal incident at this angle, which is 60 degrees, then the antenna cannot capture this radiation because it's located at its radiation null. So far, we have examined the impact of parasitic elements and how they enhance the antenna coverage without causing significant distortion to the resonant frequency. Now, let's explore the performance of the antenna when mounted on a Google Glass. So as we can see on the right, the antenna with parasitic elements are placed on Google Glass. Due to the Google Glass effect, the resonant frequency is shifted to the lower frequency side, as can be seen by the black curve. Now let's look at the radiation pattern of the antenna when it's mounted on Google Glass. For practical wearable environment, the radiation performance of an antenna can be affected by the human body and the frame of wearable devices. However, as shown by the two figures, the radiation performance is not significantly affected even when the beam is steered at different angles. This is due to the fact that the proposed antenna has full ground on the bottom plane, which helps to minimize any disruption caused by the human body or wearable device frame. Now we'll have a live demo where we'll show you how to simulate such antennas using HFWorks. As you can see, HFWorks is fully embedded in SolidWorks. So basically, once you finish creating a geometry in SolidWorks, you can just go ahead and start your simulation in HFWorks. So basically, you don't need to import any CAD geometry. So it's just simply a tab. In HFWorks, we have 4 types of studies. We have antennas, S parameter, TDR, and resonance. But today we'll focus on antennas. For almost each type of study, we have 3 steps. So first, we need to specify the study properties, apply material, assign boundary conditions. If you are interested in applying mesh control, also we can use the mesh control settings. So first, let's start with the study properties. So once you right click, so for the under solution parameters, we can specify the type of accuracy, whether it's normal or high. Also, you can specify the type of frequency sweep, whether it's discrete sweep, fast sweep, single point. You can also import the frequency points from a file. In this example, we have the start frequency, which is 52 GHz, and the end frequency, which is 68 GHz, with 51 frequency points. We have 2 types of mesh. We have manual mesh, also we have the adaptive mesh. So for instance, if you're interested in studying the temperature distribution of your structure, you simply click on the thermal coupling. So before we look at the material properties, let's look at our antenna geometry. So as you can see, so the antenna has a 50 ohm feed line. Also we have the impedance transformer, and the 2 patch elements are connected by 50 ohm feed line. Also we have the parasitic elements. In HFWorks, to apply material, you simply right click and you say apply material. So you can create new material library. You can also load your material library if you have any. HFWorks material library has a large number of materials with predefined settings. For instance, if we go for biological materials, for instance for blood, you can see the blood properties for different frequencies. So to edit the material property, you simply right click and edit material. So under the material table, we can edit the material property you want. So we have relative permittivity, loss tangent, conductivity, and other parameters. So back to our antenna. So the antenna has 3 layers. So this is our first layer, and this is second layer, which is the air, because in this case we are not considering the parasitic elements. And also we have our radiation boundary, which is the air. Now let's look at the boundary conditions. We have different boundary conditions. We have port, we have lumped port, we have lumped element, PEC, PMC, PEC symmetry, PMC symmetry, radiation boundary, signal, along with other types of boundaries. So this is maybe I need to show the air. Okay, yeah, so this is port 1, port 2, port 3, port 4, and also we have PEC1 for the ground plane, and also we have also the second PEC for the antenna elements. Also we have our radiation boundary, which is air. Also you can apply mesh control. So for example, in the definition, so if you're interested in manual mesh, so you can apply mesh control on bodies, faces, or edges. Also we can specify the element size. So now let's look at some simulation results. In HFWorks, we have what we call the antenna results table. So under this table, you can see different antenna parameters, different circuit parameters such as generalized S matrix, renormalized S matrix, impedance matrix, admittance matrix, both results. For example, for our antenna, it has an impedance of 50 ohms. Also, we have VSWR. Also, we can print versus current or frequencies. Also, you can export your results to different formats such as text, CIT, SPC, or touchstone. Now, let's look at the 2D plots. Let's start with the return loss. So as we can see, our antenna resonates at almost at 58.5 gigahertz. Next, let's look at the insertion loss. So we can see that the antennas are well isolated. So to create a 2D plot, you simply right click, you say 2D plot, and then for instance, let's say we are in this now. For this is the antenna study without parasitic elements. So let's say we are interested in the S parameter. So we add S11. Let's say now S22, S33, and S44. Next, click OK. So there you go. Also, so you can export this to different formats as PDF, PNG. Also, if you're interested in looking at your S parameters results in tabular format, you can simply click on listing. Also, we can export these results to different formats such as CSV or text file. Now let's look at the antenna far field parameters. In HFWorks we have what we call antenna far field parameters. So under this table we can see different antenna parameters such as maximum gain, radiation efficiency, total efficiency, along with other parameters. Again, we can export to different formats. Let's look at the 3D plot. So for this, so we can see the 3D radiation pattern. We can see the maximum gain. You can see also the antenna has broadside radiation. Also we have the 2D plot, 2D polar plot. So to do this, so it's to polar plot 2D. Let's say for this we have at phi equal to 0. So now, so simply see the 2D polar plot. Now, yeah, before moving to the second study, which is antenna with parasitic, let's look at electric field. So here, so we can see the electric field. You right click, you edit definition. So for this example, so all the ports are excited, so we have 0 phase. So you can specify also the settings. So for this one we choose the electric field with the mesh geometry. So to animate, you can right click, we said animate, so animate versus phase. So now we can clearly see the electric field animation at the resonant frequency. Now let's move to the antenna case with the parasitic elements. So again we have the same geometry, but only this time we have the parasitic elements, so those highlighted elements. So let's look at the return loss. So now we can clearly see there is not significant change in terms of the resonant frequency as compared to the case without parasitics. So to create this 2D plot, again we said right click to the plot. So this is with parasitic, and also this is without parasitic. So click add, so we can see those 2D plots. Also, sometimes if you're interested in beam steering, so if you edit definition, so under the far field table, so we can specify the magnitude of the magnitude as well as the phase. So for example, for this example, we're interested in steering the beam at 28 degrees. So now we have progressive phase of 120 degrees. So now let's look at the 3D. Now maybe we said edit definition. So let's start with the case of 0 degree. So now the antenna is at 0 degree. Now let's say if you want to steer it at 28. So now you can see. Similarly, we can do for the 2D polar plot. So for this example, we are comparing the 2D radiation pattern for the antenna with and without parasitic elements. So as you can see, for the red curve, which is the case without parasitic, so we can see we have a nulls. When we use the parasitic elements, so the nulls at 60 degrees is removed. So now we have a better coverage. So now let's move to the last case, which is the antenna on the Google Glass. So first we need to activate the configuration. Alright, so this is our antenna. So this is the Google Glass. It has 3 parts. So again we have the antenna on Google Glass. We have those parasitic elements. maybe I need to show the air. Also we have to show the big air around the Google Glass. So this is our radiation boundary. Again, we have the 4 ports. Let's look at the 2D plots. Let's look at the return loss. So as we can see that there is a shift in terms of the resonant frequency when the antenna is mounted on the Google Glass. So now let's look at the 3D radiation pattern. So again, let's say if you want, let's start with 0 degree and then to 28 degrees. So you can clearly see the beam steering for different phase excitation. Alright, now let's look at the 2D polar plot. So as you can see that the antenna performance does not change in terms of the radiation at different steering angles. So to create this plot, again, say right click, polar plot, 2D polar plot. So this is with the plastic glass, and this is with parasitic elements, and then again with parasitic elements 0 degree, and then you choose plastic glass, again 0 degree. So now we can see the 2D polar plots. Here comes the end of the live demo. To sum up, we have examined the antenna design challenges faced by wearable devices and showcased how HFWorks can assist us in addressing these issues. We have learned that incorporating parasitic elements can eliminate certain radiation nulls without significantly impacting the resonant frequency. Additionally, attaching complete ground on the patch antenna's bottom plane can minimize the influence of the neighboring components, such as the Google Glass frame. With that, I would like to thank you, and now the floor is open for questions. Thanks.